Okay, so welcome to this next video on the playlist on functional analysis, and again we are just exploring some areas of study regarding metric spaces. So a concept I now want to introduce is that of a separable metric space. So separability is what we're going to turn our attention to. Okay, so I'm just going to give the definition of what a separable metric space is, then we'll see a few examples of separable metric spaces, and we'll, some basic examples initially, and then we'll go on to looking at some more complicated metric spaces where it's kind of a lot more difficult. It becomes a lot more difficult showing whether or not determining whether or not those metric spaces are separable. Okay, so the definition of a separable metric space. So a metric space, let's call it a set X, sorry, a metric space is what I mean to write. A metric space, so which consists of a set and a distance function d, which is mapping the Cartesian product of x by x onto the non-negative real numbers. So metric space xd is called separable if there is a countable subset of that metric space, so let's call that countable subset S, which is dense within the metric space, i.e. S closure is the entire metric space, which is dense in the metric space, i.e. S closure is equal to the entire metric space. So that's the meaning of dense. Dense means that every point of the metric space is a limit point for the set S. That's the meaning of dense. So basically, the definition of separable says that there is a countable subset of your metric space which is dense within your metric space. So if this is a picture, here's your entire metric space. To show that your metric space is separable, what you need to do is find a countable subset of your metric space for which every point in the whole metric space, so every point, whether it's an x over here or an x within the set, needs to be a limit point of that set. Clearly, if it's in the set, it is going to be a limit point of that set. So you need to check all the points outside of it to make sure that they are all limit points for the set S. And that's the definition of a separable metric space. So clearly, initially, a very easy class of metric spaces that are going to be separable. All countable metric spaces are going to be separable. I'll write this over here. So all countable metric spaces will be separable. Countable metric spaces will be separable. The reason being that if you just take the subset S to be the entire set X, then that will be a countable subset. I didn't say that it had to be a proper subset. It can be the whole set if you like, and that's going to be dense within itself because every point of that is going to be a limit point for everywhere else. All countable subset and metric spaces are separable.